Mr. Rousseau, once again. You want to talk us about the instability of cervical disc replacement. Thank you.
Good afternoon. So my topic is instability. What is instability? I'm not going into what is instability. It's very difficult to define, and there are several definitions in the literature. At least instability is when we don't have the motion that we expected. Like some cases, maybe in extension on the bottom left or into flexion on the bottom right. That could be somehow part of instability in flexion extension. So there are many, many devices, and I think those are so different regarding the mechanical concepts that we cannot really combine all that together to discuss how they work and how they have more or less instability. As a summary from this morning, all the families are similar to the lumbar at the cervical spine with ball and socket devices, mobile nucleus, and elastic prosthesis. So the mechanical concerns for instability are the compression and shear, specifically at the lower part of the cervical spine, with a combination of compression through the action of the muscles and the weight of the head, and the shear because of the type of lordosis. And we have seen earlier that the cervical spine may have several profile. So to me, it's really different when we go into flexion, and I guess that shear has a very strong importance at the lower part of the cervical spine into flexion, depending on the weight of your head, obviously. The biomechanical concerns for instability is also the surrounding elements. The surrounding elements, mostly the facet joints, but also the incus and the PLL and the muscles, the surrounding elements are crucial for instability, even more than in lumbar, where because the cervical spine is much smaller bones with much more mobility at each level, and the influence of the surrounding elements cannot be underestimated. Specifically, the ligaments, or more largely the annulus, the lateral resection of the annulus, the posterior resection. It has been demonstrated under cadaver spines studies that every single piece of ligament that we keep participate to the stability of the index level. So instability in terms of range of motion, like an excess of range of motion in flexion extension or at least rotation or translation. But we've seen earlier this morning that the center of rotation is kind of the quality of the movement, and this quality, in my opinion, is a key point for discussing instability. The center rotation is different from one level to the other. It has been demonstrated or investigated a pretty long time ago based on standard X-rays in flexion extension, with slight differences of location of the center rotation regarding the level of the cervical spine. I've been using for a while this software, SpineView, for investigating the mobility and the center rotation. And one of these work happened to be published, comparing two types of prosthesis, one with a mobile nucleus prestige, one with a inverted ball and socket, and one with a more classical ball and socket with a ball at the bottom part, ProDisc and prestige. And we go directly to the results, showing that the center of rotation was pretty much similar below the error of measurements for all the prostheses, and mostly with a very slight differences between prostheses. Okay, and we pretty much figure out that we match the geometric center of the prosthesis with the measurements. So two very different concepts may have functionment that matches the geometric center, and the quality of motion may be respected. This work was in 3 dimensions, and this time the prosthesis was one with 5 degrees of freedom, the MobiC. We had a chance to investigate that with the EOS system. Very few patients, but all 3 dimensions. And some cases are like in the range of motion that we expect, and some other have somehow an excess of motion toward extension or toward flexion. These are some of the examples that we think were out of the normal corridor and could be described as less stable. I wouldn't say unstable, but less stable. And this, again, another example, we see that the range may be very different in an homogeneous population. And this gave us access also to something that we don't see that much, because flexion extension is pretty easy to see and to understand, but what happens in axial rotation requires much more investigation to identify these outliers that have some kind of excess of motion, specifically because of the coupling. So in this field of instability, and the topic of instability, I think that there is a real interest of the modelization, the modeling. The fact that we do some simulation helps understanding the intimate mechanisms of the functioning of the prosthesis, because we've seen that on the X-rays that we try to measure something with a very few angles, and the accuracy of the measurement is very close to what we measure. So I think this type of investigation can be interesting. We can simulate surgery on a model and simulate a different type of prosthesis regarding the radius of curvature or the position of the center rotation that can be anterior or posterior. That's kind of an old work. It's still demonstrating that with this type of mathematical calculation, we have access to more accurate positioning of the actual center rotation under the experimental conditions. And this is quite complicated, but as a summary, we're able to calculate the contact forces within the prosthesis or within the facet joints, showing that at some point, like in flexion here or somewhere in extension, you can have no contact forces, meaning that under the condition of testing, we have some kind of instability because there's no pressure anymore inside the prosthesis or inside the facet joints, which is an indirect way to qualify the motion and maybe the notion of instability. That was the conclusion of this work, showing that different devices had different influence based on the conflict, the kinematics conflicts with the surrounding elements. Still, there are many question marks, specifically on the cervical spine, because most of the work that we have accessible in the literature concerns the lumbar, and the cervical spine is very less documented. So there's a lot of room for investigation in the clinics, but also in the biomechanics. Thank you very much for attention.
Thank you very much. Thank you very much, Marc-Antoine. One questions from the audience. There exist.
Okay.
I have a question.
Thank you.
One question. Punjabi has reported, you remember, about these problems, the kinematic problems, and from my point, it was a great decision from him that only the Freedom 6 degree could imitate these different range of motion, center of range of motion, and different articulation of the facet joints in the cervical spine. Mm-hmm. That's why I think the viscoelastic prosthesis is the only one we can reproducible introduce in this cervical spine. What do you mean about that?
Yeah, well, to comment on this, the work was on Punjabi, mostly on the biomechanics based on testing with the problem of follower loads for anyone who is in this field. And that's true that I think it's easy for the lumbar to be constrained and simulate the load pressure, but the cervical is another planet with a much more motion and smaller bones, and this is more sensitive, in my opinion.
Yeah.
And I would add a comment on what you just said is about the trauma, and I'm not very familiar with trauma cases with cervical implants, but I'd rather have an implant that bounds the vertebrae together instead of having the possibility of decoaptation.
Okay, thank you.
Okay.